We present our work entitled Inverse Rendering for Reflectance Decomposition with Near-Field Indirect Illumination. Inverse rendering methods aim to estimate geometry, materials, and illumination from multi-view RGB images. Previous works attempt to model indirect illuminations reflected from different materials via spherical Gaussians, which, however, tends to blur the high-frequency reflection details. In this work, we introduce an end-to-end inverse rendering pipeline that decomposes materials and illumination, considering near-field indirect illumination. In a nutshell, we introduce the Monte Carlo sampling-based path tracing and cache the indirect illumination as radiance, enabling a physics-faithful and easy-to-optimize inverse rendering method. We implement an efficient Monte Carlo estimator and propose a novel radiance consistency constraint of unobserved rays to decrease the ambiguity. Experiments demonstrate that our method outperforms the state-of-the-art, especially in terms of interreflection decomposition. Our goal is to estimate geometry, materials, and illumination from multi-view RGB images. To achieve this goal, many methods represent geometry and materials as neural implicit fields, and recover them in an analysis by synthesis manner. However, how to decompose the indirect illumination from materials is still challenging. Most methods model the environment illuminations but ignore indirect illuminations. As a result, the interreflections and shadows between objects are mistakenly treated as materials. InRender takes the indirect illumination into consideration, but they approximate it with spherical Gaussian and not jointly optimizes it. The high-frequency details of the near-field indirect illumination cannot be modeled, and the recovered interreflections tend to be blurry and contain artifacts. We present an end-to-end inverse rendering pipeline that separates materials and illumination, accounting for near-field indirect illumination. Our approach employs Monte Carlo sampling-based path tracing, enabling physics-faithful rendering and end-to-end optimization. To avoid intractable computation and optimization difficulties, we avoid recursively tracing incoming rays. Instead, we use radiance to represent all outgoing radiance in the scene, including the indirect illumination. This results in a physics-faithful and easy-to-optimize inverse rendering process. This is our rendering pipeline. To render a camera ray intersecting with surface, we first sample incoming rays and trace them to obtain their second surface intersection and visibility. Then, SVPRDF values, indirect illumination and direct illumination, are respectively obtained by neural SVPRDF, neural radiance, and SG environment illumination. Finally, a Monte Carlo estimator is used for rendering the final results. Materials, indirect illumination, and environment illumination are jointly optimized by the reconstruction loss. Monte Carlo estimator needs to sample a large number of rays to produce high-quality results without noise, which is not affordable for practical optimization. Although some techniques can tackle the issue, many of them are inappropriate in inverse rendering scenario. For example, denoising techniques require spatial and temporal information, which is not available in inverse rendering. Hence, we apply importance sampling techniques, including cosine sampling as well as GGX importance sampling to improve Monte Carlo estimator efficiency, and use multiple importance sampling method to fuse all of them. For light importance sampling, the piecewise constant 2D distribution sampling is not applicable, since it is designed for known environment illumination represented as the 2D array. It could make each pixel of environment maps vary independently, lead diffuse albedo baked-in illumination, and cause illumination inefficient for optimization. In contrast, we parameterize environment illumination as SG coefficients. And we introduce and adapt spherical Gaussian distribution sampling as the corresponding light importance sampling technique. In addition to the re-render loss, we incorporate extra losses to reduce ambiguity. First, we directly render the camera ray using neural radiance to provide additional supervised signals for training neural radiance network. Training with observed rays alone is challenging because some locations or view directions are not observed due to occlusion. Besides, there exists ambiguity between indirect illumination and material properties, since indirect incoming rays with many directions cannot be directly observed by the camera. Hence, neural radiance is indeterminate with re-render loss alone. We additionally optimize components with unobserved rays. Although there is no ground truth of unobserved rays, the consistency of neural rendering and path tracing based rendering of the rays can be used for training. We alternatively train our framework with observed rays and unobserved rays. Finally, we train with the environment reconstruction loss for better environment illumination training. Results on synthetic data show that our method could render sharp reflection effect due to our joint learning path tracing based framework. Hence, our recovered diffuse albedo and roughness are more clean compared with other methods. Besides, by joint learning framework, our indirect illumination and visibility are modeled more accurately, so less indirect illumination and shadow are baked into diffuse albedo. Our method also has quantity improvements, especially in roughness estimation and specular reflection synthesis. We visualize the incoming indirect light for each point and present recovered diffuse albedo and roughness under both settings. Training with unobserved rays helps the decomposition of indirect light and diffuse albedo. Besides, roughness at the interstice of objects is recovered more accurately. Ablations on indirect lighting showed that without modeling indirect illumination and visibility, indirect illumination and shadows would be baked into diffuse albedo and roughness. Results on real captures show that our method estimates reasonable materials for real-world object. In conclusion, we present an end-to-end inverse rendering pipeline that is capable of decomposing materials and illumination from multi-view images, while considering near-field indirect illumination. Our method utilizes the Monte Carlo sampling-based path tracing and cache the indirect illumination as neuroradiance, enabling a physics-faithful and easy-to-optimize inverse rendering method. We implement an efficient Monte Carlo estimator and propose a novel radiance consistency constraint of unobserved rays to decrease the ambiguity. Thank you for listening.